All right, 251ers, we have ended the failed experiment of teaching that other classroom. Well, I guess the sound wasn't so bad. The lighting was horrible, although I figured out how to fix the lighting, which you'll see in this video, which is just that you have to do everything manually, and I should have known that. So actually, we'll see, but I think in this video, this might be the first video where when I switch slides, the lighting doesn't adjust automatically, which is a little bit obnoxious. If you haven't noticed by now, the microphone that I usually use is broken. So for this video, possibly the next video, sound will be slightly different, coming straight from the camera, but that's okay. Hopefully it's not so bad. There's probably a little bit of an echo because of this cavernous room in the dungeon that I teach from. But that's okay. So I'm going to try to project my voice a little bit more so that you can hear me. And also I forgot to bring my clicker, so I'm going to have to walk over and change the slide manually. That's fine. We can deal with these things. So chapter 10, as you've seen, is a bit of a mishmash of different things related to coastal processes. Some of them I find more interesting, some of them like groins and jetties. Jetties are interesting. Seawalls, less interesting scientifically. From my standpoint, I'm hoping that doesn't come across too much in the videos, but I'm guessing that it might. The good news for you, all these things are important on some level. The good news for you, though, is that these last two lectures for this chapter I find very interesting, and so hopefully that will come across in the teaching. And so I apologize if the previous few lectures were a little bit dry. That's the nature of a class. There's going to be parts that are great, parts that are less great. So this particular lecture is about characteristics of coastal waters and things like estuaries, what they look like, kind of scientifically. The next chapter is about estuaries and wetlands, and more maybe on the policy side and why they're important scientifically and also economically. Interesting. Okay, so let's get into it. Coastal waters. So beyond the beach lies coastal waters, and the defining characteristics, very simple: salinity, temperature, currents. Right. So coastal water is not very deep, so pressure not a big factor, right? Because we're not going too far off coast. Salinity and temperature are always important, and the coast is where it gets really interesting because that's where they're mixing a lot, right? You have fresh water coming from rivers, meeting full-on seawater, and big differences in temperature because you're near the land, and so there's a lot of fluctuation with the heat content of the ocean and the ability of that to change. It's a little more stable, right, than that of the land, which can alternate a little bit more because remember, land has a much lower specific heat than water does. Water has very high specific heat. So coastal areas are really interesting chemically and physically. So, and then currents, because of the winds and whatnot, also because you have heat differences over land and the ocean, that creates winds, which creates currents. So the defining characteristics of coastal waters are salinity, temperature, currents. Since the microphone is on the camera, I'm going to try to speak mostly facing the camera. I apologize if I talk facing the board a little bit. Hopefully that's not too bad. Okay. So, as we've discussed, freshwater, no salinity, less dense than seawater, right? So freshwater runoff does not mix well with coastal seawater. We've discussed the halocline. We've discussed the clines, right? Usually we've talked about these in relation to processes in the deeper ocean, in that kind of region between 200 and 1,000 meters, where you see changes mostly in density. You see changes in temperature for sure, salinity, and nutrients. Closer to shore, you can see haloclines become a little bit more prominent. Halocline represents salinity variations with depth in the water column, just like thermocline represents temperature gradients. If something is considered isohaline, that means isohaline means uniform salinity from the surface to the bottom layers. And that's what this would look like. You get an isohaline water column near shore when there's good vertical mixing. So when there's enough wind that it mixes the whole water column. And so if you mix the whole water column, right, it's like if you make a mixed drink, right, and you pour one thing on top of the other, alcohol or otherwise, right, and they're two different densities. When you first pour it, they're kind of broken into two layers, but then if you stir it up, it's all the same. That's what isohaline is. The other two options are haloclines, and they can go in two different directions. So if you have water coming in from offshore, that water is going to be less salty, right? And so you'll have less salty water at the surface, because that's going to kind of float on the surface because it's less dense. And then you'll have saltier water below. So and the region between those two is called the halocline. The other thing that can happen, and this actually, we're going to talk about this, this happens in Texas, is if you have dry offshore wind, and in particular, we talked about barrier islands, and behind barrier islands are lagoons. If you have a lagoon and you have wind, dry winds basically causing evaporation in that lagoon, you can actually have higher salinity at the top than you do below it because you're evaporating and basically creating higher salinity water at the surface. But that's not super stable, as you can imagine, because that higher salinity water, so the catch is the higher salinity water has to be warmer, and that will keep it at the surface. Because below, if it's all the same temperature, and you have higher salinity water at the surface, you know that that's going to be more dense and that'll sink. So you have to have basically the sun heating the surface waters and evaporating it and keeping it a little bit less dense because of the temperature, which would create a higher salinity surface water. That's less common. Much more common is the lower salinity surface layer. So get that one in your head. So I promised you a few lectures ago that I would show you some data from my PhD. Here it is. This is pretty basic data. This is surface salinity that was mapped during a cruise that I went on. And you can see these black lines here. This is the ship track. We do this a lot, so we basically went to the coast and then went offshore until we reached blue water, turned around, went back. And in this study, we were actually interested in nutrient cycling, but salinity is one of the things that you measure. And the reason that I'm showing you this is you can see, so the darker this is, the higher the salinity, up to 35. The lighter it is, the lower the salinity, down to 0, though we don't really have 0 salinity in the ocean. But this is Southwest Pass, the Mississippi River Birdford Delta. This is where Mississippi River is entering onto the Louisiana continental shelf, and you can very clearly see the influence of the river coming pretty far offshore, right? And even kind of here in the inner parts of these transects, you see that there are lower salinities. So it says, notice how salinity near the Mississippi River Birdfoot Delta is much lower than that far away. The river water enters the Gulf, and it actually stays on the surface due to its lower density, and it kind of spreads across the shelf on the surface and creates this layer of water with a little bit lower density and a lot of nutrients. And so this kind of fertilizes this area. And we will talk about this in the next chapter when we talk about dead zones. So salinity is one thing that impacts the coastal water column and the density structure. Temperature is the other thing. So just like isohaline indicates that the entire water column is one salinity, isothermal indicates that the entire water column is one temperature. So isothermal, the water temperature is uniform throughout the water column. It looks like that. It can be low or high. So in the tropics, right, near the equator in particular, you're going to have higher isothermal temperatures in coastal waters. Whereas in polar regions, you'll have lower temperature isothermal water conditions. Either way, pretty much the same temperature from top of the water to the bottom. And again, these are coastal areas, so they're not very deep, maybe down to, let's say, 100 meters at most. Maybe 200 meters at most. 200 meters, you have the shelf break, right? And then it gets deep and you're definitely not coastal anymore. So not more than 200 meters for sure. Probably less than that. So where we get thermoclines tend to be in the mid-latitudes. So, like where we live in mid-latitudes. We live in the subtropics. I grew up in temperate areas. Both of those places will have a thermocline. So a thermocline represents temperature variations with depth. Kind of like the halocline, but for temperature. That's right. Sorry, I was looking at this. These both say kind of like for temperature, isohaline. It makes sense. I confused myself to thinking that didn't make sense, but it does make sense, which is good. And so what happens is in the summer, when there's a lot of sunlight and temperatures are a little bit warmer in the air, then the thermocline actually looks like this, where the surface waters are a little bit warmer than the deeper waters. In the winter, the surface water, the thermocline is kind of inverted in terms of what's going on in the surface waters. In the winter, the surface waters are going to be cooler than the deeper waters. That leads to formation of ice sometimes, and this is not going to be a super stable water column, because if you have cooler water at top, if it's not less salty, which it might be in a coastal area, but if it's not less salty, then it's more dense than what's below it, it's going to want to sink. And so this can lead to an unstable water column. Regardless, it's in the mid-latitudes that you're going to see a thermocline. Okay, so and all of these things are related to estuaries, and where you have mixing of water from the land and from the ocean. So estuaries are believed to have appeared due to sea level rise after glacial retreat began about 18,000 years ago. These are the estuaries we see nowadays. If you go back further in time, there were estuaries in different places that originated at different times. There are 4 types of estuaries based on their geologic origin. Coastal plain estuaries, these form as sea level rises and floods existing river valleys. An example of that is Chesapeake Bay. I'm going to go through these definitions and then you'll see an image of each of them. Fjords form as sea level rises and floods existing glaciated valleys. Places such as the Alaska coast, Norway, and New Zealand. One of my favorite answers that I ever got on a test is I asked students where they might find a fjord, hoping that they would think, these things form in existing glaciated valleys. So if you have glaciers, it's probably cold. So where do you find a fjord? Somebody told me Mexico. Probably not Mexico is the answer, because it's not very cold nowadays. For sure in Mexico. So if I ask you where you might find a fjord, remember it's going to be places that are colder. New Zealand is far enough south, especially on the South Island, that they have glaciers. Norway is kind of classic. When we think of fjords, I think a lot of us might think of Norway. These are these really steep valleys. They're really pretty to ride a boat through in the Alaska coast. So, and the word fjord sounds Norwegian, right? I don't know if it is, but it sounds like it might be. The third type of estuary is a bar-built estuary. These are shallow and separated from the open ocean by sandbars. So this is what we find basically between barrier islands and the mainland, all along the East Coast and the Gulf Coast. Right? This is what we find. If you drive to Galveston, through Houston from College Station, if you drive to Galveston, you drive over an estuary. You're on a bridge, right? You're on a bridge and you go over kind of a low-lying coastal area. That's an estuary. That's a bar-built estuary. So, and then finally, there's tectonic estuaries, which form when folding or faulting rocks generate downdropped areas, such as in San Francisco Bay. So we've been talking about on the west coast of the US and other tectonically active areas, that if there's some tectonic activity, an uplift of a piece of land, or there can also be downlift of a piece of land, this can create an estuary, and that's a tectonic estuary. So what do they look like? Good questions, 51ers. You're always coming up with good questions. So here we have our coastal plain estuary. So this is a figure from the book. I like it because it gives you, some sort of photograph or aerial view of the estuary, and then it also gives you like a schematic kind of cartoon of what that type of estuary might look like, and it indicates whether or not things to look at. It says over here, note the different shapes. It indicates if it's deep, right? A fjord is deep. Coastal plains, not so much. Lagoons, really not so much. Indicates if it's kind of wide or narrow. And this one also indicates the tectonic setting. So, coastal plain estuary, just basically water has risen and come in over places where rivers come out and meet the ocean. So this is the best example for this is the Chesapeake Bay. A fjord, again, this is when water has come in, rising sea level has come in and filled in basically where a glacier used to be. And so glaciers, when they are moving, they cut very narrow, deep pathways. And so fjords are narrow and deep, and they're usually very pretty. It says here, fjords are steep-sided, deep glacially formed estuaries that are flooded by the sea. So in this particular one, this is in Alaska, you can see this is a glacier right there. So you can see the glacier at the end of the fjord, right? And this means that all of this water filled in here, this used to be where the glacier was, but the glacier is retreating, which is a nice way of saying melting. So the glacier is melting and leaving behind the path that it traveled, and that's being filled in with seawater. That's what a fjord is. A bar-built estuary is this space between the barrier island, in this case, this is the picture we showed you earlier. In this case, this is Tom's River. Is it Tom's River? I think it was Tom's River. New Jersey. And the mainland, right? And so this area in here, between the two, is called a lagoon, or a bar-built estuary. This could just as easily be Galveston and Houston. Or I guess this would actually be Texas City. But Galveston and the mainland Texas. Or Port Aransas and mainland Texas down there, right? So that's a bar-built estuary. And these are pretty shallow. Usually not more than a few meters deep. These can be tens of meters to maybe 100 meters, not super duper deep. Fjords are pretty deep. And a tectonic estuary can also be deep. And if you look at this picture closely, you'll see there's this kind of gray line that's disconnected here and forms the floor of this estuary, and that indicates that this basically used to be a plate that went straight across and it kind of dropped during some tectonic activity and formed a bay. And so here, this is San Francisco right here, Oakland, this is the Bay Area, right? So we also have Oakland and San Jose. It shows you the fault basically right here. This whole area just kind of dropped and filled with water, and that's how we get San Francisco and Oakland and San Jose. Okay, hopefully that makes sense. So, by definition, an estuary is going to be kind of the interface between the land and the ocean. That means that for many of these estuaries, or pretty much all these estuaries, there is freshwater meeting ocean water. And freshwater has no salinity. Ocean water has 35 parts per thousand. So there's going to be some amount of mixing. And depending on the amount of mixing, that will define a little bit what the water column looks like. So there's 4 flavors of these, but really in my mind, these two kind of grouped together, and I think for what's really expected from this course, you can kind of group these together into stratified. So there's vertically mixed, stratified, and a salt wedge estuary. I can tell you what they kind of look like. A vertically mixed estuary, these are characterized typically as shallow estuaries that have a low volume of flow. Net flow is from the head to the mouth of the estuary. That's a lot of fancy words for saying basically there's fresh water going towards the mouth, and it's because it's kind of slow, what you basically see are bands of salinities as you move inwards, or zones of decreasing salinity as you move inwards, with the entire water column kind of being mix of a certain salinity. And so if you look closely, you can see at the mouth, salinity is greater than 30. This line right here is for 30, indicating that this whole region is between 20 and 30. This whole region is between 10 and 20, and from the bottom of the estuary to the surface, it's pretty much the same salinity, and so as you go further inland, the salinity is just getting lower. I can skip to the bottom, where we have the opposite. We have a salt wedge estuary. A wedge of salty water from the ocean moves in under the river water. So these are interesting systems where you have fresh water moving towards the coast. Fresh water, if you remember, is going to be less dense, so it's going to stay on the surface. And actually underneath, that fresh water moving in the opposite direction, upriver, is salty water, and that's called the salt wedge. Sometimes there's concern about this in terms of what it might do to the water table. If you get salt in your water table, if you're drinking water, then that's not good. Salt wedge estuary is not a bad thing necessarily default, but when people talk about these, sometimes when you hear people talking about salt intrusions into the water table, this is what they're talking about. So in this case, the surface water would be pretty fresh, and you can see there's basically at the bottom towards the mouth is the highest salinity, and it's diluted as it comes in. It looks almost like this, but only on the bottom. So in the middle, we have slightly and highly stratified estuaries, and this is all just a mix of the fact that salt water is denser, and so it's going to be on the bottom. Fresh water is moving is lighter, it's going to be on the top. If they're actually stratified, if there's enough of a density difference between the fresh water that's moving towards the coast and the salt water that's below it, which there often is, you'll actually get separation of those two layers. So that's what stratified means, right? You have different layers. Strata, right? Strata is a layer. That's where the word stratified comes from. So you have different strata, different layers of salinity. It's a slightly stratified estuary. They're saying salinity increases from the head to mouth at all depths, but you have two distinct layers. And in a highly stratified estuary, you have a deep, higher salinity layer increasing from the head to mouth. And so basically, either way, you're going to have mixing of the salt water and the fresh water, and salinity is increasing towards the mouth. But there's different flavors of how stratified that is. I think that these can really be the same thing. So again, I want you to remember that you have stratified estuaries where you have two different layers, the fresher one on top, the saltier one on bottom. You could have a vertically mixed estuary where the up-down is pretty much the same salinity. You're just diluted and getting saltier as you move towards the coast. And you could have a salt wedge estuary where the salt is coming in underneath the fresh water that's moving towards the coast. And so it can actually come up into the estuary a little bit. Okay, we are going to spend the last few slides. Is that right? Oh my, we're going to run out of time. That's okay. Maybe I'll do Chesapeake Bay and see where that gets us. So I want to give you case history of one of these types of estuaries. So this is bar-built estuary. I'm sorry, coastal plain estuary. The type case for coastal plain estuary, Chesapeake Bay. It is slightly stratified and experiences large changes in salinity, temperature, and dissolved oxygen, so which makes it pretty interesting scientifically. Maximum freshwater river flow is in the spring. This is also the case for the Mississippi River. So in the US in general, the highest flow of rivers tends to be in the spring, and this is largely connected to the fact that you have all of this snow melting and entering into the water table. And springs also tend to be rainier, right? So high flow in the spring, and then waters may become anoxic, that means no oxygen at all, from May through August. This tends to be bottom water. Chesapeake Bay, if you don't know where that is, in this map right here, that's Washington, D.C. This is Virginia, over here somehow. Really? Oh, this little slice right here is Virginia. Did you know that? It's an interesting little slice. This is Maryland, Delaware, Maryland, Virginia, kind of all down here, right? Washington, D.C., if you haven't been there, is right on the border between Maryland and Virginia. It's actually its own thing, right? It's its own district. But it's on the border between Maryland and Virginia. So the reason that we're using it as a case history is it's a really well studied estuary. It's really well studied, largely, because all of the politicians, all of the federal, national level politicians, live in Washington, D.C., and so Chesapeake Bay is in their backyard, so it's pretty easy, I should say pretty easy, it's easier to convince them to give people money to study Chesapeake Bay, since it might actually affect their kids and themselves, as opposed to an estuary down here in Texas, where you have to convince the rest of the country that something in Texas matters, but they don't see it in their backyards. That is the way the world works, unfortunately. So anyway, it's a well-studied estuary. And in this map, which is from your book, it's showing you a few things. You know what? Showing you a few things. It's showing you salinity, so you have to look closely to actually see it, but it's showing you salinity contours, which start up here, and it says 10, and then 15, and 20, and 25, and so the major river flows coming from this direction. You don't have to know the name of the river, it's the Susquehanna River, but there's a bunch of rivers that actually dump in. The Potomac also dumps into the estuary, and so on one level it's showing you the salinity contours, which is interesting, so you can see that this, not surprisingly, you have some salt water actually making it all the way up in here, but on the freshwater, this is kind of slightly stratified. So on the way out, in the surface waters, you see gradient of salinity, and then on top of that, in the red here, all of this red, and the more red it is, the more anoxic it is. It's showing you where it is anoxic in May through August. The reason that it's anoxic is related to eutrophication, basically too much nutrients entering into the water, fertilizing the surface layer, which leads to phytoplankton overgrowth, and when they fall to the bottom, they're eaten and the oxygen is used to eat them. We're going to talk about that in the next chapter. So, like I mentioned, there's increased nutrients from sewage and agriculture causing algal blooms and environmental issues. That is called eutrophication, so we will discuss that in the next chapter when we talk about marine pollution. But what's important for this is what that leads to is major kills of commercially important blue crabs, oysters, and other bottom-dwelling organisms. As me, Professor Sylvan, the scientist, I am also concerned about the environment itself, not just the economics of the environment. But these are all bad things for both the environment and the economy. What that looks like, two ways to look at it. One way, this is some figures from your book, where it shows you kind of the bottom profile of land in a few areas. You can see that there's these kind of dips and little valleys. This is July 1950, this is July 1980. Be careful in life, 251ers, when you do this in the news all the time, when you're watching something, they just show you one picture of something and say, ah, look at this, that's horrible. That is called an anecdote, and it's not statistically powerful. So that if I just tell you one story, it may be a really, truly horrible story, but it does not necessarily reflect conditions in general. However, I can tell you that they're using these two pictures, 1950, 1980, but they are reflective of the broader story. And so this happens to be from 1980, but if you looked at summer conditions anywhere from kind of 70s through the 80s, it would look like this. So, and what you see here is that there's this big region of anoxic water in red where there's no oxygen, and then even here there's a 2. This is showing you dissolved oxygen concentrations in parts per million. Less than 2 is hypoxic, and so you can see lots of it. This whole area is hypoxic, whereas none of it was anoxic in 1950. Parts of it were hypoxic, and so there's probably some level of, some small amount of this might be natural. Hypoxia, especially in coastal areas, is something that happens on a small scale kind of naturally, but we've seen increases in this over recent years in many places, and that is decidedly not natural. You know what? 251ers, you're going to laugh. I actually have 2 students from this very class waiting in my office. I didn't realize what time it was. So I'm gonna finish this slide and then cut off the lecture. See, some of you do actually visit my office. Okay, sorry about that. So, but what I wanted to show you this in 2 different ways. So this is what kind of eutrophication looks like. The good news is that they threw some money at this problem, did some research, figured out why this is a problem, and figured out that's due to nutrient inputs, put some measures in place to try to reduce the nutrient inputs, and there's still some hypoxia for sure in Chesapeake Bay. There's a lot of people living there, so it's hard to get around it, but it is less than it used to be. It's better than it used to be. But this is showing you what that looks like in a different way. So this is a vertical profile in the water column from my friend Aaron Field, who published this paper a few years ago, looking at oxygen and hydrogen sulfide. And so we have oxygen in blue, and you can see this is 4 meters down to 13 meters. So again, this is an estuary. It's not super deep. This is a different station in the same nearby region, going down to 16 meters. So again, not super deep. But we see here in blue, you see oxygen comes down and it actually goes to 0. And here, oxygen comes down and actually goes to 0. And the interesting thing is what happens when you get no oxygen is the microbes, microbiology that can live there change. And you get microbes that, as a byproduct of their metabolism, produce hydrogen sulfide, which is, if you ever go to a marsh and you walk around and it smells like eggs, rotten eggs, that's the rotten egg smell. It's because of a group of organisms called sulfate reducers. They are anaerobic, so they can't live with oxygen, but if there's no oxygen, they take sulfate and they turn it into sulfide. Sulfate is something that, as you know, is a major component of seawater. Sulfide is not, it's actually poisonous to us. You can't breathe it. And so a little bit is fine. It's not poisonous if you breathe a little bit, but if you don't have oxygen, you only have sulfide, that is poisonous. And so you can see when there's no oxygen, then that's when the sulfide kicks up, and you get a lot of that. So I'm going to stop this one here. And then the rest of the chapter, we are going to talk about wetlands, basically. We're talking about lagoons a little bit and wetlands. So until then, be good people. I hope that, sorry, we're back to this. This is better than the other classroom. But you know what? You try new things, and sometimes they're great success, sometimes they're not. So I will see you in the next video. Until then, you know the deal. Be good people and read the book. See you then.